Applying coding principles to your programs can result in cleaner and more reusable code. In this video, we will look at 10 principles that will improve your code. The S.O.L.I.D acronym consists of 5 principles that each make your code more testable, maintainable, reusable, and scalable. The S in S.O.L.I.D stands for the Single Responsibility Principle, or the SRP. In basic terms, the SRP states that each class should only have one reason to change and therefore only one job. A simple example of SRP is in a school system. Let's say that we have a program representing a school with many classes, students, and teachers. For the student class, 99% of programmers will put the functionality for grade calculation, report card printing, and test scores all in the student class, violating the SRP. Furthermore, changing one system would risk breaking another, and the code would not be easily reusable for, say, another student in a different school system that isn't graded. What you should do is separate the student class into multiple classes with one job each, thus following the SRP. This creates a system that would be easier to reuse and test, and wouldn't break other code if one was changed. And now you can bring the necessary code over to a different student without hassle. The O in S.O.L.I.D stands for the Open Closed Principle, or the OCP. It says that classes should only be open to extensions of functionality and closed to modification, because changing the code of an existing class when trying to add more code could risk creating bugs. The usual way to apply OCP is with interfaces or abstract classes in Python. For example, let's say that we had a store that accepted toy guns of many types and brands. The store was selling 3 brands of guns: ammo, buff, and carbon. Our job is to add these guns to a buyer's cart. If we code a program to check for each brand using if statements, we violated the OCP. Now, if we wanted to add a new brand, we would have to change the outer code. However, if we create an abstract class that each brand would fall under, we could change the parameter type to the abstract class. So now, if we want to add a new brand to the shop, we can just create a new class to represent the brand and add the class to it, automatically adding it to the add function without having to modify its code, removing the need to remember to modify the adder code. The L in S.O.L.I.D stands for the Liskov Substitution Principle, or the LSP. It says that every subclass should be swappable with its superclass. For example, back in the toy gun example, let's say that we have a toy gun abstract class that each gun will inherit from. The toy gun class, alongside other variables and functions, will have a function that will reload the gun. Each gun from each brand will inherit the toy gun class. The problem is, while the ammo and buff guns have physical ammo that can be loaded on them, the carbon guns don't have ammo and instead rely on sound effects. So, when carbon inherits from the toy gun class, it must unnecessarily fill the reload gun. The carbon class will not be swappable with the toy gun class, which is a violation of the LSP. You may think that you can add a variable to the toy gun class that shows if the gun uses ammo or not, and while that can work, there are some problems. Firstly, code must now use an if statement to check if the gun class will not guarantee that it would have ammo, giving it a misleading interface. So it would be better off having 2 subclasses of the toy gun class showing if the gun has ammo or not, and having the guns inherited from either class. In this case, the ammo and buff guns will inherit from the gun with the ammo class, but the carbon gun will inherit from the gun without the ammo class. The I in S.O.L.I.D stands for Interface Segregation Principle, or the ISP. The ISP states that classes implementing an interface shouldn't have to get functions it doesn't need. It's basically the LSP of interfaces. Back to the toy gun example, this time in C Sharp. Let's say that we have an interface that each gun the store implements. The interface will have a function that plays a sound effect when a gun is shot, along with others. However, as ammo and buff guns already use physical ammo, they'll automatically play an organic sound. But this function pertains to sound effects being played by a little part. This function will only be suitable for carbon guns, but it's also forced onto the other guns that don't need it, violating the ISP. The solution is to break down the large interface into smaller ones. In this case, the gun interface would split into an interface for silent guns with no sound effects and guns with sound effects, satisfying the ISP. Finally, the D in S.O.L.I.D stands for the Dependency Inversion Principle, or D.I.P. D.I.P. states that classes should rely on abstractions to communicate with each other rather than concretions, which allows for decoupling. If you're confused, abstractions refer to interfaces and abstract classes that only define the function or variable and not the actual code behind them, while concretions do the work of programming the code for the function or variable. So, back in the toy gun example, let's say that we had a shooter that could shoot multiple guns by a function in the code, like ammo guns, buff guns, etc. If we were implementing the ammo gun first to be shot, we'd most likely directly refer to the ammo gun class. This violates D.I.P. as the ammo gun class is considered a concretion. Also, if we wanted to add more guns in the future, we would have to change the program class, violating both the OCP and D.I.P. By adding a common interface to each gun class, we can refer to that in the code, following both principles. The D.R.Y principle is an acronym for Don't Repeat Yourself. As the name says, you shouldn't repeat sections of your code multiple times, because if that part has a bug, you will need to go through each instance of the snippet and fix it. For example, in this program, the centimeter values are being converted to inches, but the division calculation is being repeated, which violates D.R.Y. It would be much less painful if the calculation was extracted into its own function. However, the use of D.R.Y should not be done too early, which will be discussed in the next principle. The A.H.A principle is an acronym standing for Avoid Hasty Abstractions. Sometimes we use D.R.Y premature abstractions to make the code more unreadable and complex. A.H.A states that abstractions should only be used if there is a real need for them. For example, let's say that we have a program that calculates the volumes of a wide variety of solids. If we try to apply D.R.Y to this code, we will end up with a code more illegible from the start. This abstraction is hasty because there are only two methods and there's no need for such complexity. And here we should consider A.H.A and keep the repetition until there comes a real need to remove it. The K.I.S.S principle stands for Keep It Simple, Stupid, which obviously says that you should always keep your code simple and easy to read. A common example is true and false values. We may check for an expression in an if statement and return true or false based on it. But this can be simplified by just returning the expression. Some other ways to follow the K.I.S.S principle while coding are making clear variable names and using the built-in methods when needed rather than reinventing the wheel. The Y.A.G.N.I principle stands for You Aren't Gonna Need It. It says that you shouldn't code things that you think you may need in the future. Like K.I.S.S, it also advocates for code simplicity. Let's say that while just starting coding up the toy gun classes, we try to predict the future and add things like reloading and sound effects. We should hold off adding these features and only add them when we need them. The T.D.D principle stands for test-driven development. It says that we should test code before writing it, leading to making the code have higher quality and readability. The main part of T.D.D is the red-green refactor cycle. The red stage involves creating a test that will fail due to the absence of definitions. The green stage involves creating the smallest amount of code needed to pass the test, and the refactor stage involves, well, refactoring the code. For example, we will implement adding toy guns into a customer's cart while using TDD to do so. Firstly, in the red stage, we would create the tests without defining anything. It's like writing on scrap before viewing it. As the variables haven't been defined, the test automatically fails. So we move on to the green stage. We add the definitions and code to pass the test. Finally, the refactor if needed. Those were 10 principles in coding that you should follow. Try 3, 2, or even 1 principle from this list, and your code base will be sparkly clean and organized. Also, if you want to check out my Python IDE, Cobra, and check out this short demo of my ideas, I'd love to hear your thoughts, so comment down your feedback, and I'll see you in the next video.